like to introduce Dr. Kathleen Ritterbush. Kathleen has a bachelor's from California Lutheran University, a PhD in neuroscience from USC, so she is a Southern California girl, for sure. Positions held, she's from 2008 to 2013 had a couple of different positions at USC. Then she had a NASA postdoctoral research position at the University of Chicago. And since 2015, she's been an assistant professor at the University of Utah Department of Geology and Geophysics up to today. A long list of publications. I won't spend the next hour and a half reading them. She is a faculty research advisor for both master's and doctoral candidates. Some of them she's indicated are pretty good and some just disappear. So you can ask her about that later maybe. She teaches some really cool classes such as the world of dinosaurs, mass extinctions, and paleobiology, amongst others. And her research summary statement says that she studies marine ecological transitions over long periods of time and space. She examines the sedimentary and fossil record of mass extinctions, critical transitions in biogeography, and small-scale animal-environment interactions. She's married to Amir, right here, who is also University of Utah faculty, and they have a 3-year-old daughter, which they managed to escape from, and they're having basically a wedding anniversary.
This is our 7th wedding anniversary, and we're here, so this is very exciting. Thank you.
So, without further ado, I'd like to ask you, you've already done it, welcome Kathleen Ritterbush.
Great, thank you. I am loaded up with microphones, so I usually just am loud, but you'll have to let me know if you can't hear me. Also, if I say words that don't make any sense, please stop me and ask me to turn them into words that do make sense, because before I was a professor, I used to sit there watching my professors I was assisting talk and think, what are they? They're not using words anybody understands, and now I find myself doing that all the time. Anyway, yes, I will be giving a talk tomorrow about how animals make rocks. But today, it's another of my great loves, which is trying to imagine what these fossils are telling us about what the animal was like when it was alive and swimming around or whatever else it was doing. And so the order of the day is Ammonites. We titled this Swimming with the Ammonites. And I will be investigating with you what these animals are, what we know about them, what we don't, and how well they could swim. Basically, the talk will go, what is an ammonite? We'll discuss some bets. I'll show you some experimental results, some simulation results, and we'll talk about the winners and losers in our ammonite races. But by and large, I'll get into what the animal is. People have very different visions of what these animals might be capable of and what they might do in the world or have done. Whether they were racing around chasing each other and chasing fish, or if they were just lurking and creeping. So we should back up a little bit and just discuss what is an ammonite. Well, one of the things that you could think about an ammonite is that they are fossils. They're beautiful fossils. They're used for jewelry, they're used for decorations, they're used for household items. And often the way that they fossilize includes some pearly material and some crystal material. They're gorgeous fossils. And they also come in all different shapes and sizes. They come in coiled shapes and weird trombone shapes, and some of them get quite large. Here I'm posing with a cast of this specimen. The real specimen's in Germany, but this specimen is at the cast is at the museum in Los Angeles. And so it's about the size of a Fiat, maybe. You know, you could drive this around on the freeway. And so trying to imagine what sort of animal was capable of producing this shell or a different species, this shell, or a different species, that shell, is sort of our challenge for today. Also, you could call these collectible, and you wouldn't be wrong. Ammonites are one of the favorite things that people like to grab when they're in the field. They make fossils that can be wildly abundant. Talk to Mike about that. There are places where they're just scattered all over the floor of the earth. And also there are gigantic piles of ammonites that have not even been named, studied, cataloged, or counted that are sitting in museum drawers. This is just a snapshot from the Natural History Museum in Los Angeles storage warehouse out by the airport, where they have about 7 million fossils. Probably a third of those are ammonites, and nobody knows what the heck to do with them, which is why I get to go play. And they just have drawers and drawers and drawers. So they make fossils really easily. We've got a whole lot of them. And then we get to play with the numbers. We get to crunch the numbers. This is a map that I pulled up on a website everyone can visit and play with. It's called PaleoBioDB for database, paleobiodb.org. Anybody can go make a map, make a plot of diversity through time based on fossil data from across the entire planet. And every one of these dots is a publication. Somebody said, I found this ammonite in this place from this rock at this time. They published it, and somebody put that over the last 30 years into this database. And so this smattering of fossils is just 2 different sorts of cephalopods, showing you from Jurassic and Cretaceous time all over the world. So they make beautiful fossils. The fossils are easy to find. We have a lot of them. And then we can play with the data that we have. So one of the things that we're really good at was dyeing, and also diversifying. So ammonites, among people who love them, are famous for their sort of boom and bust dynamics. In terms of the diversity and abundance, how many are there and how many different species might you interpret them to be? The answer is often an enormous number. And so if we look at the last 500 million years of life on Earth, which if you are camping and somebody finds a fossil and you can see it with your eyes, and they say, how old is this rock? You can say, well, this rock is probably from the last 500 million years, because that's the time during which we can easily see fossils. Before that, you need better technology. But if we look over the last 500 million years, there have been a whole lot of different mass extinction events, which are another thing that I and many of my colleagues study. And tomorrow we'll be talking quite a bit about these 2 mass extinction events. But if we think about ammonites, one of the neat things is that here, the little blue data, that is, now we're looking at the number of groups, taxonomic divisions called genera of these animals. And so if we look at, say, this 4th to most recent mass extinction that happened in the middle of the Mesozoic dinosaur times, the drop-off in the number of countable different types of organisms was quite huge. This was an enormous mass extinction. And with them, the ammonite diversity dropped as well. And it took quite a while for both of these animals to increase in diversity. And so they're a little bit like a canary in a coal mine. If you take all the fossil animals from the sea that are boneless, the invertebrates, from the time of dinosaurs, about 1/4 of the data that we have comes from ammonites. So they're doing a lot of the heavy lifting in how we think about life, death, and change during the whole Mesozoic era. This is an example of the sort of very highly detailed work that people can do when they're thinking about a mass extinction event. And one of the really neat things that I like working on a mass extinction is the recovery. Because working on the mass extinction itself is a little depressing. Everything dies. Who wins? It doesn't matter what you do. It's just, everything's terrible. And then afterwards, this is a very interesting interval for maybe 1 million years, maybe 2 million years, where some animals just have a really great time. The after party is really where it's at after a mass extinction. And so this is a plot put together by people over about 40, 50 years of working diligently on all the different ammonites that they could name and guessing their family tree and their large taxonomic groupings and saying, okay, there's a Triassic period that ends in a global mass extinction, wipes out all kinds of things in the sea. And then in the early Jurassic, hot damn, it's a very nice time to be an ammonite. The diversification of different groups of ammonites just goes bananas after this mass extinction. And this is about 1.5 million years right here. And by 1 million years after the mass extinction, no problem. You want ammonites? We've got ammonites. They're abundant, they're large, and they're diverse. Now, here's the thing that I always thought was funny when I was starting my PhD, working on this mass extinction, going in the field and finding these fossils. They look the damn same. Most of these have a shape that looks more or less like a coiled up snake. and the ones I've marked in blue have a more streamlined shape. They could all have the same number of coils. They could all be the same age, but the streamlined ones have covered up their previous coil so you don't see it. The snake-shaped ones are exposing the previous coil, so it's easy to see. And so if you just say, okay, well, tell me what shape everyone is, I don't care that there are a whole bunch of different taxonomic divisions. In terms of what shape are they, you've got mostly different kinds of ammonites that are probably genetically independent making the same shape. And that asks us, well, what was that shape good for? What can we learn from this? And they're large. A lot of them are about the size of a car tire. And this is a 3-pound sledge for scale, and this is one that we looked at in Nevada. So we can try to say, okay, we can see a lot about the diversity, the abundance, the size, but what might the shells of these animals be telling us? The sad news is we don't have any decent fossils of the soft body of the animal. So we have the shells and we have their modern relatives. That's what we can learn from. So we think about an ammonite. Conveniently, they have modern relatives. Ammonites' closest living relatives are the squids, the octopus, other squishy things like that we like to put on pasta. Their more distant living relative is the nautilus, which we like to put on mantles as we cut the shell open and sell it for buttons. So these being living relatives, closely and more distantly related to ammonites, sad to say, all ammonites went extinct. Just a moment for a tear. When all of the non-bird dinosaurs died at the end of the Mesozoic, so did all of the ammonites. They did really well through several mass extinctions, just almost dying and coming roaring back. But none of them are with us today. And the thing that looks kind of like one because it has a shell is alive, but it's not actually, to our knowledge of the branching changes in these lineages, it's not actually that closely related. But we get to play. Sadness. We can look at the diet of other ammonites from what we find in the fossils. So probably a large part of their diet was other ammonites. They're not sentimental. Also, this is some recent microscopy that was done where you can make 3D images of something you haven't even excavated. It's still inside the shell, but you can create these incredible images, and this team put together the mouth parts of the ammonite and found inside of it a little shelled crustacean. Arthropod, you know, little sea flea kind of a thing. So they're eating stuff in the water, they're eating small animals, and probably detritus, you know, your odd fish head or dead ammonite or what have you. And then similarly, other things were eating the ammonites. So some ammonite shells have cracks on them that have been repaired and healed in life. And if you ever find a garden snail, before you chuck it for the birds, take a look at it very closely, and you will see places on the shell where it has been damaged, but whatever doesn't kill you makes you stronger, at least for a little while if you're a snail, and the snail can repair that shell where it has cracked, where it has been damaged. We see this all the time on nautilus shells, on snail shells, and on some ammonites you can also see where the animal survived damage to its shell, rebuilt, and moved on. Some of these might have been inflicted by other sea creatures that were smaller than them, and some injuries were unfortunately fatal. Some injuries do not heal. If the air pockets we'll talk about in a minute, they have some air pockets, and if those get punctured, it's just game over. Also, they could be gobbled up whole, and none's the wiser, or smashed to bits. And again, very hard to tell. But we can tell then that ammonites were critical to Mesozoic food webs. And if we want to, by extension, say, well, what can we learn about modern squid? We know a lot about modern squid and octopus, and they certainly are important in modern food webs. Maybe that can give us a picture of what it was ammonites were up to. We know ammonites were eating a lot of different small things. We know they were food for a lot of different things. What are squids up to? Well, the short answer is it's complicated and everything. Squids are cannibals. All living cephalopods are carnivores. None of them are vegetarians. None of them are altruistic. They'll eat just about anything. They'll definitely eat each other. And squids will eat more squid in their diet the larger they get. So the larger the squid is, the more of its diet is made out of other squids. And so then this takes us back to our imagining. Somebody was asking me over here, oh, well, what did that ammonite eat? Probably mostly other ammonites, especially the bigger they got. And another way we could try to think about modern animals is we say, okay, well, All right, so ammonites are a large part of our food web. Cool. What are they eating? Each other. All right, that doesn't help me. If I want to reconstruct ancient ecosystems and I want to say, why were they so susceptible to ecosystem collapse in the face of mass extinctions? How fast could those processes happen? If we want to look at carbon cycling and energy cycling through these food webs, well, we want someplace to start. How much energy did it even take to be an ammonite? What could an ammonite even do? Something that many people learn in school is that the bigger an animal gets, the lower its metabolism. A mouse with a heartbeat, a hummingbird with a heartbeat, an elephant with a slower heartbeat. That's less oxygen per minute, that's less energy each instant that that animal per mass needs to use up. And so here I've illustrated little fish, big fish. As things get bigger, they don't need quite so much energy. Well, this little, oh, I don't have this is all from Siebel and his co-authors, from the sort of mid to late aughts. This little shape represents the size of most fish here in mass and their range of consumption of oxygen. This funny shape represents the size, big, drastic, from teeny tiny to very huge, and this is on a log scale, so we're looking at, 10, 100, 1,000 times greater in size. Invertebrates in the sea exist along many different size varieties, and they too have high metabolism per unit when they're small, and it's lower when they're bigger. Jellies are kind of a wild card. They can have very low metabolisms no matter what size they are, big slow jellyfish. Here's the trouble with cephalopods. The modern squid are fast, voracious murderers. A single squid can start out hatching out of an egg smaller than the length of your pinky fingernail and can be from that corner of the room to that corner of the room, if they're really reaching for it, And so the orders of magnitude of size that a squid experiences, and most squids that I'm showing here in blue, they're voracious murderers. They have very high metabolisms their whole lives. Whereas octopus tend to follow the more expected curve of as they get larger, they need less energy per unit. Whereas in black here, I'm showing the vampire squid and related lazy, creeping, deep sea detritivores, just eating the odd fish head that comes down every now and then. So if we simplify that, the simple question is, oh, size. Does that tell us about energy consumption? Would not in a cephalopod, not in the animals that are closely related to ammonites, and by extension, if ammonites were a quarter of the things that leave fossils from the sea for hundreds of millions of years, and they had every different kind of evolutionary relationship between them and all this diversity, trying to pigeonhole them and say, oh, well, they were all definitely like squids. Or no, they were all probably like octopus. I mean, these are just the living things, and their spectrum of demands is crazy. Things that are fast and need a lot of energy, or things that are slow, don't really need a lot of energy. We could put ammonites anywhere in there. So one of the approaches that I like to consider is to think, all right, how could this animal move? And can we break down how its motion could tell us about what it would need to do in life? And we can compare their shell to that of a chambered nautilus. Here is an X-ray of the shell of a chambered nautilus, and here is a picture of a fossil, and Mike brought some beautiful ones up here that we can see. There's a place where the body would be, and sometimes that's preserved in a fossil, and then there are these walled chambers. Well, the animal, each time they build a wall, they generally slurp the water out, and they can have air or a vacuum in those chambers. This makes them sort of nature's first little hot air balloon. Instead of swimming actively to get off the bottom, they could compensate for the density of their shell in their body by just having some air. And now they're not creeping and crawling on the bottom anymore. They could hover, and if they could hover, maybe they could move faster. All of the animals that we have that are cephalopods today have a way to do jet propulsion. You bring water in, you squirt water out. That's how you can move fast. So think of a balloon, fill it up, let it go. This is how a squid moves. This is how a nautilus moves. We presume this is among the ways that an ammonite could move. Okay, well, the fundamental problem here, and this is where the physics become just delightfully inviting, is that if they are, when they're in a hurry, they are moving away from the face. And if you are an ammonite, that means the shell is in the way. The shell's in the way. So we suddenly have this delightful physics problem. Okay, well, here's an animal, needs to do things, needs to move around, fast, slow, whatever it's doing. The shell is in the way. That shell could be protection against predators, it can be a buoyancy apparatus, but one way or another, if this guy wants to jet, he's dealing with that shell. So this allows us to ask, oh, well, based on all these different shell shapes, does that tell us different things about the physics required for this critter to get a move on? So we can think about contrasting different shapes of ammonites. Earlier I told you that across this mass extinction there were a few, in the sort of after party, there were a few streamlined forms and many forms that were not so streamlined. We can consider how these things just conceptually ought to affect the physics of trying to swim in the direction of the shell. Now, one of the issues is stability. The distribution of the body relative to the air pockets creates a distance between the center of buoyancy, which I'm showing in blue, and the center of mass, which I'm showing in red. This guy would be more stable. This one, if you think, okay, I'm gonna go really fast and jet out some water, you might like a pinwheel on accident because it doesn't have a lot of stability. And there's a lot of new, fresh, ongoing work that I have not done myself and will not present today on trying to figure out how, if we can model the hydrostatics of the interior of the shell, what it can tell us about how stable and how readily able these animals were to recover their position in water. But if we think more about the outer surface of the shell, we can think about the fact that water flowing along this shell as the animal's trying to move is going to encounter greater sources of turbulence and eddies and swirls and all kinds of weird stuff that's going to happen. This is here looking at a top view of the shell. The streamlined shell invites the water to slide past. The shell that has the exposed coils has a couple of hubs of crazy turbulence. This is something that we might expect to make the shells more of an impediment to propulsion. I like to characterize them as being shaped like a frisbee and shaped like a snake. And there's another shape that's very common in ammonoids, and that is the basketball. So we can think about the shells being on a spectrum of these shapes. And Gerd Westermann, who was a world-renowned ammonoid paleobiologist working out of a museum in Canada, who passed away a few years ago, had pointed out that there were shells of all these different shapes and that they tended to grade into each other through their growth to adulthood or through their evolutionary processes. And so this is a figure that I made when I was in graduate school, saying, okay, well, how would I characterize these things? And mathematically, over many nights at an Italian restaurant doodling on the placemats with that guy over there, I came up with this way that I could quantify and compare these metrics, saying, okay, well, these ones are exposed in their hubcap while these ones don't. These ones are very inflated while these ones are very compressed, so they're not inflated. And this guy is expanding the whirl quite rapidly while these are not. As this whirl comes around, is more or less the same size. The growth is always at the aperture, and they add incrementally just a little bit of shell, same as a snail in your garden. Okay, so the going consensus in the field at the time was that these were probably drifters and maybe these were swimmers. And these, oh, nobody knows what the hell to say. So, great, this is a good jumping off point. It allows us to say, can we test these interpretations in some way? The good news is, yes, we can. How do we work on things that are dead? However we want. We can make, using a lot of emerging technology, which is why God made graduate students, because I can say, hey, I know this is possible, you figure it out. We can make replicas of fossil shells and then manipulate those replicas. So this is a picture of some of us. This is, Lindsay is working at the LA Museum. Nick is my PhD student. I'm doing what advisors do and just smiling while they do the work. And we are scanning some specimens that Lindsay brought from Los Angeles for us. This thing that looks like a kitchen blender with the tines taken out is actually a laser scanner that is in real time constructing this 3D model of the specimen on the screen while I sit there grinning. Because this is a heck of a lot easier than using all kinds of materials to cast and produce and reproduce. We can just in real time create a 3D model, then I send Nick to the lab for a week to clean it up, and we can manipulate it. We can make it bigger or smaller, whatever size we want. It's delightful. This is an example of a couple of specimens that we made here. Is just a cast, a 3D model of a Jurassic shell. Here's a nautilus, and we sort of slapped a dumb little body analog into it. Now, we can also make idealized shells. Shells that don't necessarily exist or are limited to a particular specimen that I found. But we could say, well, if we just want to interpret the different principles of how physics move around shells of these different shapes, well, then let's do that on imaginary shells. And so one of the wonderful things about being at the University of Utah that I didn't know before I took the job is we have one of the best video game schools in the country. So I hired a video game major, and then she became a video game master student, and she built this infrastructure for us to just say, no, I want toggles. Because that's how I want to work. I either want to punch in numbers or I want toggles to play and say, no, I want more world expansion. Oh, but I also want more hubcap exposed. No, I want it more inflated. No, less inflated. I have toggles. She's also now working on a video game where you get to design your own ammonite and take it for a spin. It's not open yet. These things take years and years, but it's a whole lot of fun. She said, can I finally make a game out of it? I said, yes, you can. So then we can make these shells that are just these sort of idealized, perfect specimens that don't necessarily need to exist. Now, what do we do with these shells? Well, the good old-fashioned way of doing things is flume experiments. You get some equipment that can send water through a chute at a specific speed. You stuff your little play animal in there. You see what the water does. Here we have a picture of, this is a water chamber that they use to teach physics students at the university how these things work. And we have a little device that can measure the force. It's a little force transducer on a stick. And so you crank up the speed of the water gets going, it pushes the model, and the model pushes on the force transducer. And you can say, yes, it is a big thing in the way of the water. The shell is a pain in the butt, all right? The other thing that we can do is a really exciting emerging field known as computational fluid dynamics. And this is pretend water. It's simulations in a computer, where effectively we can take the exact same model, instead of printing it in 3 dimensions, this is some really nice medical resin, instead of printing it, what we can do is set that model inside of an imaginary computed space where every little divot of water is segmented off into little polygons, and then the math of, hey, how should this water move from point A to point B? The computer can do that in 2 million little polygons inside of something about the size of a large fish tank. Again, this is why God made PhD students. My student Nick has figured out how to do all of this, working with, now one of our best partners is an engineer who I met in a jiu-jitsu class who works in sewage systems. We met and I said, hey, what do you do? I'm an engineer. Oh, what do you work on? Oh, I work on sewers. And I said, wow, you work on sewers. Tell me more. Do you use ANSYS Fluent to do computational fluid dynamics? She said, nobody ever gets excited when I say I work on sewers. That's usually the conversation ender. But she's now a co-author with us, which is awesome. And that's Yoonji Choi. So she's been helping Nick fine-tune all the physics of how the water should flow through these little aliquots that they've been divvied up into. So before I move on, I did want to pass out some samples. Please get these back to me. But these are, you can just pass them around. These are some of the 3D pins. The ones that are made out of sort of chintzy plastic just cost a couple bucks to make at any local library. And the ones that are made out of a slightly nicer, heavy material are made out of some, here, I'll pass a couple to the back. Okay. This one's an allosaur claw, but you know, here you go. The resin ones are actually made at the medical printing library facilities at the University of Utah. If you wanted a nice kneecap, this is what you would use. So we can use those materials to be impervious to the water. And so now we can consider, place your bets, all right? You've got some ammonites in your hands, there's some ammonites up at the tables. The first experiments that we did was try to capture the low-hanging fruit here. Kind of an average, typical Joe ammonite. An ammonite that's definitely more compressed and showing some of its coil. A word for this is serpenticone, because it's shaped like a snake, right? And then a really inflated one. A word for this is sphericone, because it looks like a sphere. So if we take the most inflated one and the one showing its coils that's more compressed than this guy, and we run them, it took a long time. We ended up finding the medical resin because the little plastic ones that are made out of extrusion, oh man, they take on water. I was putting epoxy on them. We just went through like a million steps and we found these resin ones. Perfect. So we can run those in our equipment. And the question is, all right, our interpretation based on work that other people have done. We're not the first to do these experiments. These experiments have been done in the 60s, 70s, 80s. But we're the first people working on this project at this time who have all this technology to play with to just easily whip up whichever shells we want and produce them in the ways we can. So, okay, based on previous experiments, this guy, it should be harder to push through the water. This one should be easier. All right, here's Nick. Here's our force transducer. He's very high tech. We've got everything attached, and this little animal is in the water flow chamber. Okay, let's go. Let's get some data. The x-axis here is swimming faster. Now the shell isn't going anywhere, the water's going somewhere, but 6 to 1, half dozen of the other. The idea is the animal is fixed in place as the water comes rushing, whoopsie-daisies. As the water comes rushing around it, the idea is if he was going jet, 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 this is the drag that would be caused by this shell. So that's the premise. We can say if the guy is trying to swim faster, and then it's going to be harder to push. So let's look at some results. Ah, we got some results. Delightful. This black one up here is a sphere. And then for here, I'm showing you this serpenticone and the sphericone. All right. Blue data. Now the error bars are that we repeated these experiments over and over and over. And it turns out, oh man, these are hard to do. No wonder nobody does it anymore. The temperature of the room changes everything. Turns out the force transducer is kind of a piece of crap. It's a big pain, right? But it's neat because we can visualize the difference and we can measure the difference between the drag that is suffered by this animal when trying to swim versus this one when trying to swim. Now here's the rub. I'm showing a water bottle here, but imagine holding just a little water bottle in your hand. That is about how much force we are measuring. And these shells are the same ones I'm passing around. They're about 5 centimeters in diameter. So if you're that little fellow and you need to jet somewhere, if you wanted to go 20 centimeters per second, well, that's 4 times your body length in a second. Zip! Well, it would cost that much energy. That's how hard you would have to push. A, that's really hard to push. B, maybe you don't need to go that fast. Maybe we should calm down and say, well, what if he's just going 1 body length per second or 2 body lengths per second? Oh, somebody's trying to get me. Ha-ha. Right? Now, you can see the trouble with the experiments on the equipment that I had. When all these things start to get dangerously close to overlapping at around 10 centimeters per second, which is double, sort of 2 hops per second. The trouble is this tank is too damn small. It should be much larger. It should be much, much, much larger. This stick is kind of big, and the force transducer, the best it can do to measure things is about at the threshold of anything we can even get it to measure it all. So the errors on this make it a huge pain in the butt. Enter the reason we switched to computational fluid dynamics. Computational fluid dynamics, you can do whatever you want. You put it in imaginary water. So first question should be, all right, I see your imaginary water and I raise you, is it any good? So here I'll show you what we can synthesize. Purple is a perfect sphere in our simulations. These red dots are this shell shape that we made in our video game equipment. These black dots are this shell shape, way more streamlined. And then these green dots are a chambered nautilus that we scanned the real shell, and then we put, in all of these we're putting kind of a dumb body on it based on mimicking some experiments that were done by Dave Jacobs, who's now a professor at UCLA in Los Angeles, and he just put, poor guy, I mean, he had to deal with actual casts of real fossils, so to put a little body on there, he just put some modeling clay on it, called it good. So our version of the little digital modeling clay is just a little schmutz of the body. Anyway, these are simulated data, and for the nautilus, you'll see, in terms of the drag, and this is in log scale, so 1, 10, 100, 1,000. It makes a big difference whether you're a big life-size 14 centimeter nautilus, or if you're a little fella, 5 centimeters down here. This is the same as these sizes, okay? So here we're seeing, okay, our nautilus is making more drag to go to the same speed compared to this really streamlined guy. And this is all simulated. Of course it looks clean. It's pretend. How does this stack up to real data? Well, for the analytical answers of what a sphere should be, we're not terrible. These are Jacobs' experimental data. I think we look like we're doing a pretty good job. Now, I'll note, Jacobs' experimental data really peter out, same as ours, right around that 10 centimeter mark. You try to go slower than that, you're in a world of hurt. And the nautilus data that I'm plotting here is a variety of spots because these guys were also different sizes. This is by an amazing British study where they basically, and this study was not trying to measure drag on a nautilus shell. They wanted to do something about the duty cycle of the push and recovery of the jet of a nautilus. So they got a big cube tank, and they put a live nautilus in there, and they waggled a shrimp at it, and it had to go chase the shrimp, and then they'd waggle the shrimp again. So it's not what you'd call a clean experimental setup in the same way that I'm trying to measure drag, but hey, data's data, and when it came out, I was very excited. Okay, so I would like to compel you to have a little faith. Our simulations are very relevant to what we would get in experiments, and they're at least the right order of magnitude. I think they look pretty good. Now let's return to my dilemma of saying, okay, well, I'm measuring water bottle sized forces filled with water, by the way. So I'm measuring pretty big forces at pretty high speeds, but I want slower speeds and I want lower forces. Well, with the simulations, we can do that. Because by discretizing these water pockets into little, conceptual nuggets that we can measure, we can visualize and then estimate the cost of all the little eddies and swirls that form around the shell. And now I'm moving my water bottle up here. We're looking at all speeds that are lower than 20 centimeters per second and all drag forces that are smaller. This is good, this is what we want. We can move it into a log scale on both axes so it looks pretty straight. It just cleans it up, makes it a little easier to see this lower level. Okay, well now what are we talking about? Now we could be talking about forces about the size of a small apple in terms of how hard you have to push. We could be talking about forces the size of a paperclip in terms of how hard you have to push. Hey, paperclip size forces are a lot nicer, and that's if you want to go just a fraction of your body length per second, right? Now for scale here, I put some cherry blossoms. 5 centimeters per second is the rate at which cherry blossoms fall. It's also the rate at which a sloth moves. So we're not talking racing here, but we're talking about, would you hold up that small apple just for everyone to see? Beautiful. So if you want to move about as fast as a cherry blossom through the water and you've got one of these shell shapes, you're looking at about an apple's worth of force. All right, cool. Now, this brings us into visualizing more specifically this question I brought up at the beginning. What is the cost of this hubcap? If we say, oh, well, all these shells are the same size in terms of their overall diameter, well, how much of that hubcap is exposed? Here, 60% of the diameter of the animal is hubcap. Over here, it's less than 20. Okay, well, what does that do to your physics? It depends. Depends on if you want to go fast or slow. Here is a beautiful visualization Nick made of those eddies. Now what we're doing is slicing through the animal and looking at it from the top, because you can slice the imaginary water any way you want. And looking at it through the top, this guy with all of his coils showing, that one is probably actually this one, it's generating a lot of eddies in there. This one also has some eddies, but they're much smaller. Here, the brightness of the color is the speed of the water. And you can see water just jamming right past the edges of the shell, but water that gets stuck in those pockets or behind the shell becomes added mass, becomes weight, becomes a whole lot of slow stuff that is literally going to drag you down. Now, if you want to go slowly, it turns out it's not that big of a deal. This is if these animals are each moving 5 centimeters per second using this shell. And here, each data point is representing that shell shape I had before. So these guys at 5 centimeters per second, and this is on a linear scale here, not log. So if they just want to go 1 body length per second, okay, well, the difference in force looks pretty negligible in terms of how much drag this generates. What if they want to go 3 body lengths per second, 15 centimeters per second? Okay, now we're going to go from 1 apple of force up to 2 apples of force, and it makes a really big difference. Now that hubcap makes a real, same shells, same speed, but now that's when that hubcap effect starts to really kick in and be a pain in your butt. If you're small and you want to go fast, or if you're large and you want to do just anything. I was warned that there would be, plenty of physicists and engineers. So we're going to think about this size and speed problem together by using Reynolds numbers and coefficients of drag, which is fun. Even paleontologists are allowed to do math. So this is a typical specimen that we find in this early Jurassic coiled up shape. Okay, not only is it a coil, it's also very, very big. The coefficient of drag is a handy number that we use to say, okay, all things being equal, how much is your shape the problem. How much is your shape contributing to drag? So if you are like me and you're obsessing over the new Jeep Renegade Trailhawk and you really want a new vehicle, but you also want some fuel economy and you're on Car and Driver all the time and you're looking at the stats, you're going to be looking at coefficients of drag. I'll tell you it's not good on a Jeep, all right? It's not even good on one of those little Fiats. It's better on, you know, half of you drive Subarus. You know what I'm talking about. The coefficient of drag is not how many horsepower do you have or how big are you. It's given all those other things being equal, how is your shape contributing to how hard it is to push. Now here's the fun thing about coefficient of drag. You get a discount. If your Reynolds numbers are higher, a Reynolds number, oy vey, basically how much turbulence is there? Is it all smooth sailing? You know, you turn on the faucet, it's just right, you're gonna fill up your water bottle. Ah, damn, the water's just flapping all over the place. You just hit that turbulence. So smooth, and then going into turbulent, and then going into airplane flying. We're talking about really different Reynolds numbers. And it turns out that ammonites, their size, from about the size of a garbanzo bean up to the size of a Fiat, they produce shells that are going to force the whole range of Reynolds numbers to be relevant throughout the life of one individual or across the spectrum of individuals. Also, if you want to go faster, you're kicking up your Reynolds numbers. Now here's the fun thing. Your coefficient of drag, whatever it is, it will go down if you're in a higher Reynolds number regime. Think about, you know, doing some like jazzercise in the pool, you know, it's kind of hard to move. And if you just really get trucking, you're actually able to move a little bit more smoothly. All right, if you kick up into a turbulent, the eddies are going around you and they're going past, you actually, your shape is, you get a discount because you're not dealing with friction anymore, you're just dealing with your profile shape, which could be broader or narrower depending on how long you've been doing the water jazzercise. So if we consider the data in this way, same data as I was showing you for drag, but now it's in terms of coefficients of drag and Reynolds numbers. Here are some of my shells, my inflated sphericone, my streamlined shells, right? They all get a discount, but look, the sphericone does not get such a big discount. Kick him up into the high Reynolds numbers. Oh, hey, and this is on a log scale. 1,000, 2,000, 5,000, 10,000, 20,000, 50,000. Hey, kick him up into high Reynolds numbers. He's bigger, or he's faster, or both. And he gets a discount, but it's not great. Kick this shell up into higher Reynolds numbers. Who doggies? The way that the shape is contributing to drag has really decreased. And again, what causes this is the breakoff from the friction around that shell, making it just about an equal pain in the butt at low Reynolds numbers. When the water is flowing very gently, it's dragging around the shape. But once you get up into the high speeds, all that you're pushing is that profile, and it's that pressure drag that's doing most of the heavy lifting. So this discount has a different shape depending on your shape. Here's the fun part. We can add some more shells. So Nautilus. We can add shells mimicking the experiments that have been done. Hey, look at these fellows. These are the ones I was just showing you on that chart in linear fashion, looking at drag. And noting that, oh gosh, well, when they're faster, it costs a lot more drag. You could also say when they're larger, it costs a lot more drag to have this hubcap showing. Look at this. Here, at low Reynolds numbers, small and or slow, who cares? Whatever, it doesn't matter if you are this streamlined shape or this snake shape, it doesn't matter. But if you kick it into higher Reynolds numbers, if you want to go fast, then it matters. Then it is going to cost you. You know? If you drive a Jeep Renegade, no problem. 5 miles per hour, 10 miles per hour. You want to really get on the freeway and pass somebody, it's going to start to cost you. And this higher Reynolds number transition interval is where this hubcap on these shells starts to kick in. But again, we can, we're talking about animals that were making big shells in this early Jurassic after party. They didn't have a choice once they reached that size of what Reynolds number regime they were going to be in. If they're moving at all, they're in big Reynolds numbers regimes. And they look terrible at it. This is another way to visualize the same thing. Here's our spectrum of shells again, being some of these data points here. And here, it's just drag again, raw drag. Hey, how hard do you have to push? Yellow is harder, cool colors are, it's easier. Okay, well, in this regime, going 5 centimeters per second, hey, all these guys have less drag than over here. These guys have less drag than over here too. You can tell there's some weird wiggly woggles happening in the middle, especially when we get to the higher speeds. If we put this in terms of coefficients of drag, it starts to look real different. Now we're seeing perhaps adaptive peaks or adaptive valleys where, ooh, don't be that shape. Do not be that shape. If you want to be fast, that's a real bad one. That's bad, that's bad. That's pretty good. These guys, streamlined. That guy, ooh, stop it. No good. All right? Now, obviously, well, not obvious to everyone in the room, but painfully obvious to me every day I wake up in the morning, this work is really just getting underway. This is Nick's 4th year of his PhD, next year's his 5th, he's gonna finish, you know, and what he has done in that time is build me all the toys and build me all the things, and build me all the infrastructure for us to start testing these things, and this is as far as we got. We've just started to crack the surface on it. But it does allow us to think about what shape might have to offer. And anyone who has raised a child and watched them learn to talk and still bump into doorways, or who has raised themselves and decided how to spend a budget, or has looked at animals and evolution and realized that everybody's got to spend their budget on something, and it's not always high performance. There's a give and take with all the things that nature has to offer. So, I think I've been thinking about this all wrong. Sure, these guys are terrible at swimming, or rather, by the time they're big, probably not very good at swimming. They're not efficient, say, compared to somebody else. Well, maybe they don't care. What else you got? If you've got that shell shape, what else you got? So now we can think about some growing. Same shell, but it's going to grow. And our sort of little mascots here again. If you want to get volume, I don't care about speed, I don't care about what I'm doing, I don't care about looks, I don't care about flash. I just want to house this delicious body. I want to house the body and all the gonads and make babies like crazy. Then for every aliquot of shell material that I budget, the ones that are going to grow the fastest are the spherocones. I mean, no surprise, spheres end up with a lot of volume per surface area unit. And even though we're dealing with a coil and all that stuff, hey, these guys, winner, winner, chicken dinner, if you want more volume to house your body, he's your man. All right? They win. Now, what if you want diameter? And I was reading about some ecology literature saying, look, the best way to not get eaten is just to look big enough soon enough. So by the time you get into sub-adulthood, other predators say, oh, can't eat that one. It just looks, you know, like a snake will kind of size you up and be like, I couldn't swallow it, you know? And so if we think that animals could actually be served ecologically by just looking bigger from profile view, it doesn't mean they are bigger, because we know they're not the winner in volume, but if they just look bigger, like, hey, I can't eat that. Hey, the winner is this guy. His world expansion rate is really high. It doesn't translate to overall volume. It also is really nice for speed, so he gets a twofer, right? This guy's pretty good for speed and acceleration, and hey, he looks big. Cool. Way to size out of the menu. All right, our lowly spherocones, our lowly oxycones, our serpenticones. What do you got, serpenticone? Venter. Well, what the hell is venter? The tube is longer. The thing that this guy wins by about 20% is as he grows, if I say, okay, here's your same aliquot of shell material to put on your body, his tube is longer than the other guy's tubes. And it took a while to say, all right, you know, this I get, it's volume, this I get, you look big, this what the hell good is having a longer tube? This is what I think. So we're presuming they're cannibals. They're eating each other a lot, especially the small ones. That's what's for dinner. Well, maybe having a long tube allows you to hide in that long tube. Now, this isn't any good if a vertebrate wants to eat you. They'll just crush you to death, or bite you, or shake you, or what have you. But if what you're most worried about is another ammonite, and they need to grab your soft body and yank it out, then having a tube that is more than 360 degrees, the length of that coil, which these guys are. The tube length also changes with these different morphs. So these guys, if their whole body chamber was there, his body chamber would go all the way back to here. And this would all be whole for the body. I don't think he needs all of it. It's not a whole lot of volume and he doesn't look that big, but I think it could be a feature that allows them to just hide inside that shell. which is only good for certain kinds of predation, namely other ammonites. So putting that all together, it could be that these guys are what I call successful slackers. They're not amazing at swimming. They're not the most ecologically advanced, incredible thing that ever lived, but there's a whole lot of them and everybody's doing it in terms of this simple coiled shell shape. It's easy to make to get a coil real fast, and then once you're big, it doesn't matter if you can't swim very well. All you need is wait for a spawning event and just eat all the babies you can catch. So this then being a less romantic, but I think more realistic imagining that I've illustrated of what some of these Jurassic seas that make rocks like, because this, oops-a-daisies, heavens to Betsy, that's not what I wanted. Oh no, where'd you go? Oh no, it quit. Stupid Mac is stupid. Here, I'll just get it back up, but we're almost done anyway. You son of all the monkeys. Jackson, Ammonites, that's me. Oh no, which one is it? Huh. They should be the same. Yeah, I get it. Oh no. Husband, can you come do it while I talk? He's a PC guy, I'm a Mac, it's a mixed marriage. Yeah, anyway. I have a couple other illustrations of kind of before the extinction and after the extinction. But this is PowerPoint, it's in PowerPoint? It's in Keynote. It's in Keynote, and Keynote crashed.
It's an application.
Yeah, this is fun. This is real fun. Super great. Anyway, it's challenging. I think one of the fun challenges about being a paleontologist trying to work doggedly on a particular question is, and it's on the desktop, the actual file. Yeah. Sometimes we keep so focused on that question we think, yeah! So the little, yeah, play. Cool. And then I can, is it gonna crash?
It's gonna crash.
Oh, ha! Okay, and then I think I can jump to the end. Jump to the, you bastard. All right. Yeah, so quick rehash. Anyway, a paleontologist can get too focused on making their PowerPoint slides work, or trying to get their experiments to work, or trying to jump ship and then do the simulations, and try to say, okay, well, maybe swimming isn't the end-all be-all. It's still really important. It's still really good information, and the shell shape has a lot to teach us. And I think also paleontologists get in kind of a pecking order. Oh, my animal could eat your animal. My animal was better than your animal. My animal was faster than your animal. And I think it's okay if a lot of our animals were just mediocre. I mean, you know, it's not survival of the fittest. It really is survival of the minimally fit. And let's repeat after me. Survival of the minimally fit. Survival of the minimally fit. It's not survival of the fittest. Look at pandas. Look at serpentaconic ammonites. You don't have to be the best. You can settle for pretty good in life. And especially if you're pretty good when you're little, that's fine. You don't have to be the best. So this is what I wanted to point to, and I accidentally exited it. This is a rock that I took a picture of. It's in a museum in Lehigh. This is what early Jurassic rocks look like. If you go to England, you know, this is what early Jurassic rocks look like. These guys were extremely successful. And I don't think they were doing much. I think that they were lazy. I think they were successful slackers. So if we contrast the Triassic, before the mass extinction, filled with coral reefs and filled with ammonites of every different size and shape, chasing and going after each other, and then we bring it around to the early Jurassic. And it's just sponges that I'll talk about tomorrow. They're horrible, but they make great rocks. And the ammonites are probably just enjoying the 2 million year hangover that is the aftermath from this mass extinction. So with that, I would like to thank my family and all the other people who've helped me do this work. And I'll take all of the questions you guys might have. Thank you.
Naively, I was thinking that for some reason that they were building up like gas inside these tubes, and then they were blowing it out. And so, is that
it's
part of anything? Their ability to kind of accelerate and then
so the gas inside the chambers, I believe from all the physics that we know to date, it would not be able to transfer well enough to be part of the propulsion. But the debate has been raging for a century over whether that gas could move fast enough to change buoyancy. If anybody's been scuba diving or attempting to be scuba diving or pretty bad at scuba diving, you know that adjusting your buoyancy very carefully is the difference between life and death, and it has some real heavy feedback loops. You adjust it a little bit and you're going to the moon. So my interpretation right now, and I have a postdoc who's going to come work with me and build experiment tanks to test more of this. He works on the hydrostatics. I really think that the shape of the little squiggly lines you see on the side, which are the walls where the internal chambers meet the outside, I think that those shapes have a lot to tell us about the physics of the buoyancy of the animal. And I think that once we get that piece better understood, it'll really help us, again, not just think, oh, well, here's a shell, I guess it's bad at swimming, I guess it's good at swimming. There's going to be some feedback between the ones that also have the potential to take advantage of those changes. So it's not a dumb question at all. They are dealing with a different amount of water to propel themselves. They take that in and squirt it out. Yeah. Other questions? Yeah.
So the Ammonites survived the Permian-Triassic extinction, all these others.
Barely.
Yet somehow the KT extinction, they didn't, and
Yeah.
other cephalopods did.
Yep.
Can you
Why?
talk about that?
It's a good question, and it's an interesting one. So the extinction that I'm the most familiar with, which is sort of at the beginning of dinosaur time in the Mesozoic, the worst mass extinction ever, makes the difference between the world before dinosaurs. It had trilobites. Those are charismatic. Yay, right? It's a world with trilobites. Ah, good on ya. And then the post-Paleozoic world, you get yourself some dinosaurs, right? Well, that world was also full of mass extinctions. A mere 50 million years after the worst one of all time, you get the end of the Triassic. I think only 3 genera of ammonites survived that mass extinction event. Anywhere in the world. And nobody can be the guy who points to, oh, well, it was this one here. We have them in these rocks. I work with geochemists, and they say, oh, you're working on rocks across the boundary. Give me the same species before and after so we know the chemistry's right. I'm like, girl, it's a mass extinction. I can't do that, right? So they were almost obliterated during the end Permian, almost obliterated from the face of the Earth during the end Triassic. Given another 150 million years having a heyday, there are mass extinctions that seem to affect the Ammonites more than anybody else. So there's one, the end of the Jurassic, beginning of the Cretaceous. That's a mass extinction if you talk to an Ammonite person. If you talk to another kind of scientist, who cares? So they were really susceptible to collapse. The chambered nautilus, which if you've ever seen one swimming, is a dopey character. There's nothing to write home about. They can outrun you if they need to, but they're not doing it on the daily. They're still alive. They and their ancestors, Nautilus were around the whole time. For some reason, they didn't get whacked at the end of the Mesozoic. I think the best thought on this currently is that it has to do with the metabolism, and it has to do with reproduction, it has to do with shell mineralogy. If you've had a rat problem, you know about our selection. Those guys reproduce real small, real fast. Versus K selection, if you've had a pet elephant, you know, it's a hard thing to raise. Or maybe, I don't know, a cow, right? It takes a while to raise a cow, takes a lot of energy. Nautilus are like cows and ammonites are like rats. Ammonites just babies, no big deal. And they went entirely extinct. So some of the people think that the particular environmental challenges that struck at the end of the dinosaur era allowed Nautilus to squeak through. Because of their reproduction, because of their eating demands, stuff like that. We'll see. I like to wait 10 years and then see what people think again. Any other questions? Yes?
Would your modeling situations on the computer take into account the trailing tentacles and body parts of your animal? And I know water that would fit down that could maybe, if they were detritus eaters, just like bring little tiny bits directly to them?
Ooh, you know what? Nobody has suggested to me the garbage disposal catch vent behind them. I like that a lot. That's the reason I give talks, because everybody else has really good ideas and I can go test them. I've never thought about that being a detrital collection setting. The short answer is, oh yeah, the body length and position makes a big difference. So far, the size and the shell is making a bigger difference than just how far extended the body is. But also, it's very tough in the methods we're using. It's very easy to tell, very easy. I make Nick do everything. It's very easy for me to tell Nick to do things that are fixed in position. It's much more difficult to deal with something gelatinous, or, you know, they're not gelatinous, they're muscular, but something that's flexible. But this is where the experimentalist I'm getting comes in, because that way you can get some sort of first-hand knowledge on things that are more flexible from experiments a little more easily, so you can even observe. Also, it's been suggested by Michael LaBarbera, who has been a pioneer of a lot of these things, that those eddies could also help them sense and smell and sniff, help their sniffers out. So there's a lot more than meets the eye. The biggest thing that the junk in the trunk is going to do, though, is add mass, which if you're trying to accelerate is a huge pain. But if you want to just coast and get the most out of your jet, it's actually awesome. We think a lot about animals just kind of moving straight like a fish, but these guys are jetting. So they want to jet, and they've got a lot of added mass they need to overcome, but then they can just kind of cruise and maybe enjoy that garbage disposal behind them. There was a question over here. Somebody, yeah?
Yeah, what do you think finally did the Ammonites end?
Oh, the end Cretaceous mass extinction appears to be, you know, a combination of climate, just mayhem from this giant rock from outer space impacting Chicxulub. You've seen the bumper stickers, Chicxulub for President 2020. A big impact from outer space hits the Yucatan Peninsula and jettisons a whole lot of soft carbon material into the Earth's atmosphere, which we're learning by experience. Jettisoning a whole lot of carbon material into the Earth's atmosphere changes the climate conditions really quickly. There's also a heck of a lot of volcanism going on the opposite side of the Earth at the same time, and a lot of people are studying if there was a feedback loop there or not. But whatever took out all the non-bird dinosaurs also nixed all the last of the Ammonites. None of them made it through. They're all toast. All right, well, anything else? We can probably talk over books and beer. Thank you. Oh, you have something.
Real quick, so you see these collections of, in the rock, all these Ammonites. Why don't we see as many as there were, as many things that are eating them? Or maybe do you see these hashes of broken Ammonites, chewed up Ammonites, you know, the mosasaurs, plesiosaurs, ichthyosaurs, and everything else we're chewing on?
Short answer is two reasons. One, it's mostly Ammonites eating Ammonites. They're face grabbers. They're just ripping each other out of the shells. It's mostly Ammonites eating other Ammonites. In terms of the number of things, the other reason is that actually when it comes to biomass in the sea, if you picture like a food pyramid on land, you got lots of grass, a whole bunch of deer, and a couple of wolves. It's the opposite in terms of biomass and carbon turnover in the sea. You've got a whole lot of Ammonites, but biomass-wise, there's not actually that much material. And you've got some gigantic lizard monsters, ichthyosaurs, plesiosaurs, mosasaurs, gigantic animals that are holding a huge amount of biomass. As individuals. They're basically cruise ships, you know? And so, yeah, just full of poop. And so you don't find that many ichthyosaurs for as many Ammonites as you find. And, I mean, you do at Ichthyosaur State Park where they're all flopped on top of each other, but it's a rarity. You know, also those things are hard to fossilize. Ammonites are super easy to fossilize. They make their own gravy. They're already made out of carbonate. You put them in some carbonate mud, voila, you got a limestone. So they're kind of doing it themselves.
So, Kathleen,